thanks a lot. And we're far from the end of this event, but since it's my last lecture and I'm leaving tomorrow, I want to thank Ralph, David, Matthew, and Fanny for putting up this event. It's really great, and I truly enjoy it. And I hope you still do, also after this lecture. And thanks also. Yeah. Now it feels like the end of the conference almost, yeah. And thanks also to Antonio and Michael for serving as TAs. Very helpful. Yeah, and no, okay, let's.
Excellent, thanks for this.
Yes, you can do this globally as well. All right, so I was almost done last time, giving a sketch of the proof of higher property T in the case of lattices in simple Lie groups. But I want to go back and wrap it up. And I put up these notions that I wrote at the end of my talk, the definition of the filling volume. So the situation was you have a cycle, and cycle now means singular cycle, Lipschitz cycle in a space X, simplicial complex that you give a metric, say every simplex is like the standard Euclidean simplex, or it's a Riemannian manifold. And then the volume comes from the Riemannian volume. And then you look at all the you look at all the chains beta that fill this alpha and take the minimal volume. Right? So if this index D is 2, then we have a one cycle. So think of a loop in X, and we're trying to fill that loop efficiently. So in a non-negatively curved space, you expect that it can fill it quadratically somehow in the length of the loop. And then we build a whole function of the space by looking at all the cycles that have volume smaller or equal to some number v, and look at the filling volumes of all these cycles and somehow take the supremum. So that gives us some function whose asymptotics tells us something about the space. And then it turns out that if you take for a group gamma some space X on which it acts properly and co-compactly, then the asymptotics of this function doesn't actually depend on the X. And you can define this, or the asymptotic class of this, as somehow the filling function of the group gamma. And can do this for every degree D. And these are the higher filling functions. And I already mentioned then that there is this theorem so you can certainly correct me on the history. And when I took this, that I write Gromov-Wenger, here is because I'm not really sure about the exact history, but that's what usually people do. And definitely Wenger gave a beautiful, very short proof in great generality, which I recommend. So it's really a little gem. I don't know about the original argument. And it says that if X is ket 0, D at least. I mean, D at least 2 is somehow the smallest case we care about, filling in loops. And then this function here is asymptotically bounded by V to the D over D minus. Let's check. So if D is 2, then we have something quadratic here, and we're filling in loops here. So that's correct. And now if you apply this to co-compact lattice in our simple Lie group.
So in other words, your clicking cases were worst? Your clicking cases were worst?
My what?
If X is Euclidean, it's the worst.
Oh, Euclidean. Sorry, I didn't understand. Yeah.
Is that right?
Yeah, that's correct. Yeah, yeah. So if we are in this situation, co-compact lattice, then we can take as our model space here the symmetric space on which gamma acts co-compactly. And so this is same asymptotically as the symmetric space here. And this is a ket0 space, and somehow not really interested in the exact thing here, but it's definitely polynomial now. Polynomial function or bounded. Everything that's bounded by a polynomial is polynomial from here. Right? And now the question is, since we're dealing with polynomial cohomology, of course, we're interested what happens for non-uniform lattices. And there was a breakthrough in 21. Yeah, don't. Maybe put it here. So the breakthrough result was by Leutzinger and Young. So if you have a non-uniform lattice, should be irreducible if it's semi-simple, but we're talking about the simple case anyway. And let's say D is below the rank, the real rank of our group G. Then they prove same thing. They prove that gamma they prove that, sorry, this order, they prove that this function, which cannot be defined via G mod K because gamma doesn't act co-compactly on G mod K, so you have to find some model space, and there exists some model space. But whatever you take, this is well defined, but it's nevertheless the same asymptotically as this. Below the rank, and it's not true above the rank. So above the rank, this is exponential or can be exponential. And that's somehow, that's the crucial input in our theorem. I mean, that's one crucial input, but that's the crucial input for this. If you remember last time I had this diagram with all this comparison map between polynomial cohomology and ordinary cohomology, and also with this Shapiro maps. And somehow what was missing was that this comparison map from the polynomial cohomology of gamma to the ordinary cohomology is an iso below the rank. So it's not so important that this is exactly the same as the symmetric space. So somehow you can go to much more combinatorial setting. You can take any nice model space X on which gamma acts, some nice model of the classifying space, and then you know somehow also combinatorially it has polynomial Hyardean functions, and then this model of the classifying space, or from its chain complex, this chain complex can be used to compute both these cohomologies, and you will get that they are isomorphic below the rank. And then somehow finishes this diagram we had last time and gives you at least a Shapiro isomorphism below the rank. And then you can conclude somehow the vanishing of this cohomology, below the rank from the vanishing of G. All right, so I think I'll leave it at that. And now I want to say something about applications. Of higher property T. And the first, well, we'll see whether it's the only one, but definitely hope to be able to complete this. Want to say something about finite approximations of groups. So let me first set the stage, what I mean by that. So this is something that has to do with this topic of whether all groups are Sophic, whether there are Sophic approximations and variations of that. And the general setting for this is we have a countable group. And we have a whole sequence of metric groups. So these are just groups, and they come with a bi-invariant metric. And then there is this notion that you can approximate such a group by this sequence. Let me define this. Gamma is approximated by this sequence if there exists a sequence of maps phi n from gamma to gn. And this will be called an asymptotic homomorphism if it satisfies the following properties. So the first is that, okay, maybe the very first, let's say that it's kind of normalized, so 1 goes to 1. The second is the most important, that it's asymptotically, it's like a homomorphism. So for every 2 group elements in gamma, when you look at the distance of phi n of the product to the product of the images, this should get smaller. And somehow the way, since you remember at the beginning of this week, we fixed an ultrafilter. It's still fixed. So this is 0. Right, so this is, of course, there are variations of that. You could also say the whole sequence. And so, I mean, there are variations of this. But why? Let's formulate it like that. And then there's also built in some injectivity. Because, I mean, so far we could map everything to 1, and that's a bit boring. So there is a built-in injectivity, and the way to express this is as follows. So if you look at the image of phi n g for an element g which is not 1, then, yeah, this should be in the limit greater than 0. So that you avoid this trivial situation. So there are 3 main examples, probably more, and I'm not like the total expert on this. But there are 3 main examples of these sequences of groups that are of interest. And one is when you take for Gn the symmetric group on n letters. And here you take the normalized Hamming distance. You just count the number of positions for which the 2 permutations are differ and divide by n. That's one example. The other example is you take unitary groups, finite dimensional unitary groups, and you take the Hilbert-Schmidt norm. I'll say a word about this in a second. And the third is very similar. But here you take the unnormalized, also the Hilbert-Schmidt norm has a built-in normalization such that if you have a permutation matrix and view it as a matrix here, they have the same norm. But you can also take the unnormalized, and this is usually called the Frobenius norm. I'll write it down in a second. And so you can look at all these sequences and now ask, what does it mean that a group is approximated for these three families? And for the very first family, this is sophicity. So this means gamma is sophic. And here it means that gamma is hyperlinear. Well, and here there is no cool name. It just means that gamma is Frobenius approximated. But somehow one of the long-standing questions in group theory is whether every group is sophic. And it's open, although there are candidates. And we'll talk about candidates. Another long-standing question is whether every group is hyperlinear. If it's sophic, then it's also hyperlinear. It's a bit weaker, again, because you can fuse permutation matrices as matrices in UN. And that's a variation which does not, there is no implication here. The reason we study this variation is because we can say much more about this. So, and okay, about hyperlinearity, there is, we know a bit more by now. We know that there are results that indicate maybe not, because hyperlinearity of the group is equivalent to something it's called hyperlinearity of the von Neumann algebra of the group. We don't know whether group von Neumann algebras are not hyperlinear, but we know that there exists type 1 factors that are not hyperlinear. But we don't know whether they come from groups. So, but there are, yeah, there is work that indicates, okay, I think most people believe this is not true, that every group is sophic or hyperlinear, but we don't know. Yes.
Is that enough to consider also groups with quasi-invariant metric for these measures?
You mean instead here, instead of bi-invariant metrics, quasi-invariant?
Yeah, like the difference of the...
What do you mean by quasi-invariant? The difference is what exactly?
That the difference between, let's say, G1, G2x minus distance, no, like a quasi-morphism, more or less.
Yeah. Okay, I don't know. I guess, I mean, there are various ways, since everything has to hold in a limit, to build in more constants and more flexibility. So maybe we can discuss later how exactly, but probably. Okay, so yeah, let me define this Frobenius norm for you. There was another question?
Here. Yeah. So the definition of sophic is that it's approximated by the symmetry.
Yes. If there exists an asymptotic, yeah, if there exists an asymptotic homomorphism into that family, yes, then it's sophic by definition. One definition of sophicity, and there are probably 100. They're all equivalent. Right.
Excuse me?
Yeah.
Sorry, it's a bit of the same question, but why do you need the bi-invariant? Why not just left invariant measurement? Okay, I mean, one stupid answer, if you want, is that the examples we mostly care about do satisfy it. But somehow when we try to do certain limit constructions, when we want to ensure that these limit constructions give you groups again, you need this bi-invariance. Okay, so do you mean that if you have this, then you can maybe like define the law on the ultra limit of the GN?
Yeah, and we will come to that. Yeah, okay. Yeah, something like that. Yeah. All right. Okay, so maybe I put down this question. I said it, and maybe most people know, but okay, so there is question: is every group, every countable group, sophic? Actually, was that Gromov who asked that first? I'm not sure.
He certainly asked.
You certainly asked, right? It never hurts at this location. But I'm not 100% sure. I mean, maybe also Benji Weiss was. Yeah, could have asked it as well, right? For hyperlinearity, I'm more confident that this was Alan Kohn. And all right, to finish this board, let me maybe put here the definition of the Frobenius, which is just an L2 norm. Just the L2 norm on matrices, and the Hilbert-Schmidt you would normalize by n, similar as here you would normalize by n, by the matrix size. All right. So I want to discuss in this lecture mostly a work of 4 people: De Chiffre, Klebsky, Lobotsky, and Thom. And I want to discuss the relation between what's called stability and T2. So what is stability? Definition. Gamma is stable with respect to one of these choices. If every asymptotic homomorphism is close to an actual sequence of homomorphisms into these groups. So it's a stability is a rigidity result. If every asymptotic homomorphism of gamma into this sequence is, and let me say in word what I mean, is close to a sequence of, don't like this chalk, let's say of true homomorphisms. In close, you could, for example, again, express via the ultra limit that for every group element, somehow the distance between phi n in this asymptotic homomorphism and the nth term in this sequence of true homomorphism goes to 0. Yeah.
If we call it an asymptotic homomorphism, why do we ask for some sort of injectivity?
Here.
Yeah, but
why? Why? Oh, because otherwise you could take just the map to the, you would get trivial examples. You want to exclude trivial examples where you map everything to 1 in each step. I mean, you could define it, of course, but then this would not be an approximation. Right? So you want something like in residual finiteness, for example. So residually finite group would be in particularly Sophic, and you would take these finite quotients and somehow if you want, the symmetry groups on these finite quotients.
So the definition you wrote for phi n is more like the definition of an asymptotic embedding?
Embedding, yeah. You might also want to call it embedding, yeah. Yeah, yeah, yeah. I just stick to the terminology they use, and they call it homomorphism, but it's an asymptotic embedding, yeah. All right, so their theorem is the following.
So can you say the close again? The definition, the closing definition.
Oh, it means that, so there you have your asymptotic homomorphism. It's a sequence of phi n's. And now there is a sequence of psi n's, of true homomorphisms. And somehow, if you fix a group element and take the ultra limit, their distance becomes 0 in the limit. Yeah. So here, very nice theorem. So they prove if a finitely presented group has this property T2, so vanishing of the second cohomology with unitary coefficients, then it is Frobenius stable. And so I said, maybe historically we're most interested in these questions because they're so prominent, but somehow we cannot answer these questions. And of course, you're looking for partial results, or results that at least somehow enlarge our understanding of the subject. And so you work with this Frobenius because you can actually prove something, and they found the first example of groups that are stable under this kind of approximation. And why are we interested in stability results? So we are interested in stability results because they give us counterexamples to the existence of approximations. So here is an observation which is very important. If gamma is Gn dn approximated, and now I allow for Gn dn one of these three, doesn't matter which one, and is oh, sorry, I should formulate it stable. If gamma is Gn dn stable, not approximated, sorry, and is not residually finite, then gamma is not approximated. So you just search for a residually finite group which is stable, and then you get, in that case, an example of a non-Sophic group. Again, we don't have examples of that. I will write down we have examples of non-residually finite groups that are Frobenius stable, so we know that at least in this norm we cannot approximate groups. And what is the reason for that? Well, if you have this sequence of, so suppose it is approximated, right? Then you have, because of the stability, your approximation, your approximate embedding is close to a sequence of true homomorphisms that also in that sense become more and more injective. And every linear group is residually finite. So if you have an element it will, in your group, it will map non-trivially to some of the UNs by a homomorphism, and it will sit in a linear subgroup, namely the image, and so you can map it further non-trivially to a finite group. So just because linear groups are residually finite, they cannot be approximated, because then, yeah, you would get this. Was that okay, or was that too quick?
So this is specifically for GNDN, one of the three sequences?
Yes, because they are linear groups, right? So input here, linear groups are residually finite themselves. And so what they constructed was they had to construct, so at that point, so this was also before I proved this stuff with Uri, but at that point you of course had Garland's theorem, and of course they appealed to Garland's theorem, so they needed to construct somehow a lattice in a non-Archimedean situation, which is non-residually finite. And then from Garland's techniques, which had to be, everything had to be adjusted a little bit, you get that this group has also T2. So cannot write down the example now, but their theorem is there exist such groups. Maybe let me now just put the initials. There exists, as a consequence, and they did it for the Frobenius norm because somehow that's the setting that can be done. There exists a finitely presented group that is not Frobenius approximated. And I hope that it becomes a bit clearer in the course of the talk that somehow what you would need to go from the Frobenius norm to hyperlinearity and sophicity is a kind of non-abelian higher property T. So some form of higher property T with non-abelian coefficients. But we'll see in the course of this lecture how this looks like. And I also want to mention that in a collaboration with Shmuel Weinberg and Alex Lubotsky, Uri and I showed this for central extensions of the symplectic group, which is an example I can write down. So the pullback of this lattice in the universal cover of SP2 and R, for example, there are other examples, is not, one knows it's not residually finite, and by similar methods you can show that it's not Frobenius approximated, and somehow what the group SPn2n has, it doesn't have T2 with these brackets, it only has T2 with the other brackets, and somehow you have to work around their method a little bit, but most of the hard work is here, and then we find a work to somehow also work with these examples. So of course there are candidates also for non-Sophic groups, but nobody knows.
For the observation, do you need gamma to be finitely generated?
Say again?
For the observation, does gamma have to be finitely generated?
I don't think for this observation it has to be. No, I think if you just look at single group elements, it doesn't have to be, but it will be in our setting, yeah. So I want to prove this theorem and this theorem, I mean this theorem. Because it nicely connects what we did in the first two lectures. I mean, at least partially. I will prove it, not completely. Right. Usual problem. Yeah, I think here we are. All right. Proof. Let's say idea. Modulo some details of this theorem. So first of all, if you have an asymptotic homomorphism, to un, everything equipped with Frobenius norm, then you can write down an actual homomorphism using ultrafilters. So what is the map here? And what is the ultra product construction? You take the product of all the UNs and here there is no, like for Hilbert spaces we looked at bounded sequences. Here it's really just the complete product, and then you divide out following subgroup where n are the sequences that go to the identity. In the Frobenius metric. So Gn minus the identity Frobenius is 0. And here, of course, you go using this phi n, so the whole phi n's. And this turns out, because somehow the homomorphism defect gets smaller and smaller, this turns out to be really a homomorphism and embedding of gamma. And this is the thing we want to improve to an actual homomorphism, or to a sequence of true homomorphisms. Now, to do that, I want to first somehow define a variations where I fix somehow the growth rate at which this happens. So let me define the following, maybe a bit more technical definition. So for a sequence of positive real numbers going to 0, we define following variation of this n, and the notation will be n of big O relative to this ultrafilter and relative to this sequence of numbers. And these are all elements in the product such that this difference here is big O relative to omega epsilon n. And what does this big O notation mean? It means that there exists a constant such that this un minus the identity is smaller than C times epsilon n for omega almost all n. So it's like this, but somehow we want to fix a specific rate going to 0. And very similar, in a very similar fashion, you can also define what is little o with respect to this ultrafilter, right? It's just when you look at epsilon n inverse times this should go to 0 in the ultrafilter sense. And then this is the notion of little o, and of course it sits inside this bigger group here. And so the thing is, which I don't want to prove, requires a little argument, but the thing is that because our gamma is finitely presented, it's actually possible to fix a specific rate of epsilon n's going to 0 such that this homomorphism actually lifts to the analog where we replace n by this. So without further argument, but since gamma is finitely presented, this is what they do in their paper. There is a certain rate or convergence rate, I don't know how to call it, such that phi n lifts to a homomorphism, and let me call it by the same notation. Let me not distinguish, where you go to the product of the un divided by n big O epsilon n. Okay. And now you want to improve. And you want to improve using group cohomology. So how do we want to improve? No, let's see. I think I can erase what sophicity is. So the idea of their proof is it's like two-step. Not you don't improve this homomorphism or this sequence of phi n's directly to a sequence of true homomorphisms. It's a two-stage process. So first you want to improve in the following sense. So you have your gamma, then we have this map to this product modulo n big O epsilon n. And somehow here you have the same with little o. Right? And you want to improve in a first step to that. So the homomorphism defect gets somehow better or worse. I don't know how. I mean, it gets better. You approximate better if you lift to this group. And so that's what you want to do in the first step. And here you have a group extension of admittedly very wild objects. But somehow what's the kernel of this? The kernel of this projection is, of course, the quotient of these two. And so this is what we want. And now you remember probably the second lecture of my course, where we had a homological or cohomological criterion to solve these lifting problems. So you had on the right an extension. You had a homomorphism to the quotient, and you wanted to lift it to homomorphism to the middle. And the obstruction was given as the element in the second cohomology of gamma with these coefficients that corresponds to the pullback extension along this. But in any case, whatever the definition of the obstruction element was, if the second cohomology of gamma with coefficients in that guy is 0, then you could lift this. This was the statement. So we want the obstruction for this lifting lies in this relatively wild coefficient where the action as a gamma module is via the map to here and then conjugation on this thing. That makes this into a gamma module. But there is one thing that you should check before. This kind of cohomological obstruction for solving these lifting problems, this was for abelian modules over this quotient group. So before you start this whole thing, the question that arises is this abelian? Right? And then you could proceed with this mechanism. So let's check that it's abelian. It's not obvious that it's abelian. So answer is yes. And here is the reason. So you want to look at a commutator in this group. So let's look at the commutator. And let's look at the distance to the identity. So if I forget it, I probably will forget it. From now on, we're only talking about the Frobenius norm. And so the T and the T is actually a whole sequence, right? So T is Tn, S is Sn, and they lie in this group. And there are sequences of unitary matrices whose distance to the identity element is like big O of epsilon n. And somehow, to show that this group is abelian, we need to show that this commutator and this difference to the identity is like little o of epsilon n. So let's rewrite this distance. We can rewrite it as Ts minus St. This is where we use bi-invariance, for example. And now the trick is you rewrite it further as T minus the identity, S minus the identity, minus the other way around, S minus the identity, T minus the identity. And then you see you get Ts minus St, and the minus T minus S gets cancelled by plus S plus T. So this is smaller than 2 times T minus the identity times S minus the identity. And that's a crucial step, which is not true for the Hilbert-Schmidt norm. So this here uses that the Frobenius norm is submultiplicative. So you can push it. If you have this normalized Hilbert-Schmidt norm, then you have this 1 over n, you have some, I don't know, 1 over n square. It doesn't work. But for the Frobenius norm, this can be estimated above by this product. And that's somehow the one distinguishing thing that we use about the Frobenius norm that we don't have for the normalized Hamming distance or the usual Hilbert-Schmidt. So how to conclude? Well, we know this is big O of epsilon n. This is big O of epsilon n. I mean, I didn't write the Tn and Sn, right? But somehow in this norm. And so this guy is big O of epsilon n square, which is certainly in little o of epsilon n. Okay, so that's the proof that this quotient is in a abelian group. And now we can apply our cohomological machinery, and the obstruction for lifting lies in this group. So the goal should be that this group is actually 0. Because you never know what is the obstruction element, right? To show that something vanishes in there, you better show that the whole group is 0. And for that, we want to apply higher property T. But for that, we need more. We need that this is actually not just an abelian gamma module. We need that this is a unitary gamma representation. So that's the next question, which I will sketch. Why is this a unitary gamma representation? Or maybe even a bit less, let's just look at why is this even a Hilbert space, right? What's the Hilbert space structure? So what's the Hilbert space structure? And yeah. So next question is this a unitary gamma representation? And I just indicate why it's a Hilbert space very quickly. So what we have is so on that side I have this. And remember, these guys, again, there were sequences in unitary groups. And on that side, I take now actually an ultra power of Hilbert spaces, but of finite dimensional Hilbert spaces. And what I take is the Hilbert space, the Lie algebra of UN, equipped with the L2 norm, which L2 normal matrices, which corresponds to the Hilbert-Schmidt norm, of course. And I claim there is an isomorphism here that equips this group with a Hilbert space. And one of the exercises is to show that it's not just a Hilbert space, but it's actually unitary. So the gamma action that comes from going from here to there and taking the conjugation action is actually gamma representation. As far as I remember, you use the submultiplicativity again. So the map is, if you have an element, the Lie algebra, so that means that like this, then it is mapped to this sequence. And again, an element is a sequence. And it is mapped to the exponential function of epsilon xn, which starts as identity and then you have higher terms. And somehow the higher terms, I have 1/2. So And somehow, as we've seen already here, somehow the higher terms really don't matter. You can show this is an isomorphism. And this is somehow ultra power of finite dimensional Hilbert spaces. And this equips this guy with a Hilbert space structure that makes this into a unitary representation. And so we can finish by saying, okay, gamma has T2, so this group vanishes. So let's say this is star. So finally, T2 implies that star is 0. And so what you somehow achieved in this is not yet somehow the ultimate result that we can take any asymptotic homomorphism and improve it to a sequence of true homomorphisms. But what we've shown is that we can somehow the quality of this sequence in the asymptotic homomorphism, we can always improve it from big O to little o. And the last step in the argument is the step I want to skip, because this is not a step where somehow here everything we did somehow featured. In the last step it doesn't, but it's still a little bit subtle. So the way they finish this argument is by a kind of maximality compactness argument that you take, but it's a bit more subtle than I say. That you somehow take already the best asymptotic homomorphism that you have. So in some sense you cannot improve it further, but then this argument shows you can improve it further. So there is a maximality slash compactness argument at the very end that finishes the job that I don't want to do, which is actually a bit tricky. But this is then how they somehow finish this argument and show that a group with T2 is Frobenius stable, and then you just need examples of non-residually finite groups that have this T2 property, and then you have these examples that are Frobenius, not approximated by asymptotic homomorphisms in the Frobenius sense. And now you understand also my remark, maybe better, that I said that to go at this sophicity question, what you want is a kind of non-abelian higher property T, or at least T2, because for the unnormalized Hilbert-Schmidt norm, that's exactly the problem. Since this is not submultiplicative, you can still write down this thing. I think you can also do the last step that I didn't talk about, but somehow this is non-abelian. And it's not even so clear what is second cohomology non-abelian coefficients. It already starts there, so somehow it's a little bit unclear. There are people who somehow worked out this non-abelian setting, at least the language and the setup for H1, but I think for H2 is a bit unclear. But that's somehow the slogan that you hear sometimes, you need this non-abelian theory. And so I see it's 5. There is a second application in my notes, but I will skip it and just end here. So, thanks.
Don't you have these criteria, like this criterion for these lifting with abelian H3, even for non-abelian groups?
This thing about cross homomorphisms?
I vaguely recall some maybe it's about like some criterion about existence of extensions by non-abelian groups using H3 in the center and the abelianization.
And looking at the map in the outer automorphisms of the kernel and something like it. There is something like that, yeah, but you're right, and I think it's also in Brown's book probably, right? But it's very hard to handle this thing because you cannot, I mean, like cohomology is something we can compute sometimes, but somehow there are tools, and somehow for this, yeah, apparently so far it didn't work, yeah. And I know that there is something, I couldn't write it down, what you said. I know where it is, I know where to look it up. And I actually know almost, I don't know a situation where this is really used, this non-abelian. Maybe Matthew?
No,
No.
but I think you have like something only abelian, even for non-abelian groups.
You mean if the kernel is non-abelian?
Yeah, the kernel is non-abelian, but you have some criterion that uses only cohomology of like abelian groups associated to it, like the center and the and I don't remember the details, but like you need some H3 or something.
Okay, then I don't know right now. Probably forgot, but let's talk after. Yeah. Okay. Now I see. Yeah. Yeah. I don't know.
Yes, right. So this is not really on the talk of today, but I was wondering how much of the vanishing results that you gave and on the methods to compute cohomology can be used for non-unitary representation, like LP spaces, something.
Yeah. So LP is very, very different. It can, as a mini short answer, it cannot be used. Because, for example, it starts with you can't take an orthogonal complement of a subrepresentation. That's at the very first a huge problem. There is something you can say. There is an application of higher property T. No, sorry. I mean, it's somewhat a phenomenon. I'll tell you something that we actually use in application, geometric application I did not talk about. So if you have a property T group, then from a theorem of Bader, Garland, and Monod, it follows that if you take an L1 space, this is L1 space is just really, you take a measure space, doesn't have to be finite measure, just a measure space, and you have a measure preserving action, and then this is 0. So for L1 spaces, you also have this vanishing of first cohomology if gamma is T. Classical T. And somehow what we used with Uri is that also just from T, not from higher property T, you get that H2 of this is Hausdorff. And that already gives you interesting applications, and probably more applications would be doable if you know that higher property T gives you vanishing of the cohomology with, for example, L1 spaces. And I'm a bit optimistic about this, that you can prove at least substantial partial results. But in general, there is no direct somehow way to go from L2 to LP. There was some.
Yes, that's the universal covering of the symplectic group you mentioned. Is it residually finite?
This is not residually finite, this group. And that's why you get this consequence here. Yeah. So this is the linear example of, okay, there is a theorem that this is not residually finite, but it is not.
Could you just give a hint about the other application?
All right, so.
I quite like it, so the chair will allow it.
Okay, so I will not talk about this because that's a longer story and the application behind that. But the other application I can do is very quickly. So it's actually my notes. Thank you for that question. No, but sorry, don't worry. But somehow there's this famous theorem of Borel from '74 that somehow the continuous cohomology of SLN are trivial coefficients. Let's take R or C, and here you have the restriction map to SLNZ. Or you can also take Q. It doesn't matter. Is an iso for I smaller than n over 4 or n minus 1 over 4. I forgot. And the thing is that this guy you can compute. As I told you, there is for trivial coefficients interesting cohomology. So this is an exterior. Did I write down what it is? It's somehow an exterior algebra in generators E5, E9. So it's 4i plus 1 up to a certain point, depending on n. So this is computable, even as a cohomology algebra. And so you can compute this cohomology in a certain range. And the thing is that this stable cohomology of SLNC was somehow important, because from that result he concluded that the K-theory of the integers rationally is, what is it? Whatever K-theory is, right? So it's only, there is a Q in if I is 1 mod 4 and it's 0, I mean I equals 0, it's also Q, but everything else is 0. And so that was this application, and somehow, let's not care about this, but somehow this computation of the stable cohomology, you can use our theorem and improve it to n-1. Because basically this cohomology, we now have a Shapiro, so you can somehow induce the trivial representation up to a representation of here without changing the cohomology. But in this trivial, right, if you induce up the trivial one, then you have a representation of that group, which is constants R plus something that doesn't have invariance. That guy that doesn't have invariance vanishes. The only thing remaining is this, and this is then isomorphic to this in this range. And so you get this cohomology improvement of this cohomology computation. And you can allow more general coefficients. And another thing, let me just say this, is that's a bit crazy. If you see this, this is just a reproof of a theorem of Borel, but I think it's in the end easier, or more geometric group theory. I mean, this is high-powered whatever. But if you take the cohomology in all degrees of SLNR with trivial coefficients and restrict it to the usual cohomology of SLNQ, this is an isomorphism in all degrees. And this is because you use S-arithmetic groups with more and more primes. So there is an S-arithmetic statement like this, and you use more and more primes, and the rank goes to infinity. In the end, you get this result. That's somehow kind of rigidity. You have a co-cycle with no continuity on SLNQ, and somehow in its cohomology class, it's automatically there is a continuous representative, and it comes from SLNR. So that's a statement that Borel and not only Borel, and they proved it also to prove something about K-theory, but I don't understand what they proved. But it's funny somehow that the continuity doesn't play a role in this setting. So applications of cohomology to cohomology. I hope you're happy.
You just have something for that you don't have continuity for SLNR? Cohomology for discrete?
Oh, yeah, that's, what was it again? That's something very different. Yeah. That's still something different from that, yeah.
Okay, well, sort of, well, yeah, go for it.
Well, just one question. So first, it's kind of twofold. So the first is, I won't repeat the name, but DC GLT theorem. Is it like constructive, or did they give some explicit?
Well, I don't know.
Yes.
Are these guys constructive? No, as the proof, I would say it's not. Yeah, but the group itself is there. So there's a construction of the group, and you can understand the group. The reason I didn't write down the group is because I cannot as easily write it down as here. Mm-hmm. But this is, they construct a group, and in a kind of a central extension of a lattice in a algebraic K group, K being like QP probably for some P, And so you can write it down.
It's a concrete group.
It's a concrete group,
okay.
But the proof is, of course, somehow ultra-filter.
And would you mind like telling us how the SL2 and SP2 and Z tilde shows up in your case? I mean,
so I'm just saying that somehow at some point you play around with property T of both the extension and the quotient. And somehow difficulty here is that this group in the quotient, it doesn't have T2 with this. It has T2 with the round brackets. So there is a second cohomology class. And so somehow you cannot just do what they do. You have to play around. But I don't have a catchy phrase somehow to say how you get around. But somehow this is what we do. It's much less deep than what they do.
Okay, after 5 hours of lectures, let's give a round of applause.
Thanks.